All right, I'm going to dispense with the introductory part and just get right back to it here. We are on page 320. Page 320. And we're talking about energy efficiency. I don't know how long this is going to go. I was hoping to add electricity to the mix as well, but we'll see how it goes time-wise. All right, in the process of energy efficiency, you remember learning the second law of thermodynamics, that a little bit of energy is lost every time that there's an energy conversion. And energy conversions are happening all the time. The type of energy that we use and the quality of the energy that we use, varies depending on the task. It's all about the task. So I think I mentioned in the last video, coal is not a very good solution for the task of transportation because we need to be able to go really fast, really quickly. So that requires a liquid type of energy source like gasoline. So you wouldn't want to have to throw an extra chunk of coal in the burner and then wait for that thing to catch before you could get moving. So coal's not a good solution really for transportation, but it is a good solution for boiling water. So that is kind of the application we came up, for instance, when it comes to coal. Gasoline, of course, is better when we talk about fuel. Now, these different fossil fuels, these different non-renewables, each have their own negative. And as we go through these different videos, that's going to be your biggest task. In fact, you probably ought to make a little table for yourself of the pros and cons. And I think at the end of the chapter, there's a summary, pros and cons table that you should really take a look at. All right, there's some terminology in this section in the textbook, so let's go over that quickly. Embodied energy. Listen, this is just like that concept of externalities that we've talked about when it comes to products. Embodied energy is the energy it takes to get the energy that we use. And this is becoming more and more of a debate and an issue as we talk about some of the shale and fracking, the use of natural gas for energy. Sometimes it takes a tremendous amount of energy to bring that energy source that we want to use to a usable end. Take a look at this diagram and you'll see what I'm talking about. All right, so here's the coal. Think of how much energy it takes just to get it out of the earth. Whether it's, and I'm not just talking about the fuel for these tractors and backhoes and all the rest of it. But think about the electricity in the buildings where these guys are working. Or the electricity for the lights in the mine. The list just goes on and on and on. All of that needs to be accounted for when we talk about cheap, affordable energy. Of course, it usually isn't. Oh, and by the way, there's energy lost all the way along the line. Now that coal's got to get transported, it's got to get processed, and then it needs to be burned in order to make electricity. Here's the turbine that I've been talking to you about. So it makes electricity. And again, every one of these energy transformations lose some energy as heat. And then eventually, of course, you get the electricity at your house. All of this extra energy that's being efforted is called embodied energy. All right, the second bullet here is about something, this EROEI, the energy return on energy investment. Okay, now I've never seen this concept questioned either on the ACE exam or the AP exam, but I think it's worth thinking about, because it helps you understand how this embodied energy concept works. Look, the idea is there's the energy that you obtain from the fuel in the numerator, and then there's the energy invested in the denominator. Now, obviously, the energy that you get from the fuel in the numerator needs to be higher than the number in the denominator, or else it's not worth doing, right? And that's one of the problems that we're running into when it comes to some of these new methods that we're trying, like fracking. And again, we'll get into that later. So let's say a pound of coal gives us 100 joules of energy. Remember, joules is our unit of energy, but it takes 5 joules of energy total to get that pound of coal to the power plant to turn it into electricity. Well, then it's got an EROEI of 20. All right, it's just that simple. You'll never be asked to do a calculation like this, but when you compare other forms of energy, this term becomes pretty valuable because you can compare different energy sources based on how much effort it takes to get it out of the earth. And there's a blue box on page 321 that takes a look at the efficiency of traveling, for instance, when it comes to these things. So, the idea is different fossil fuels have different returns on investment, and it all depends on the job that we're going to try to do with those fossil fuels. This table is on page 321, and here's the point I was just making: finding the right energy source for the job. Coal isn't necessarily the right energy source to heat your house, right? Shoveling coal into a furnace downstairs isn't the best idea, right? Especially when we can find other techniques and other ways. And so that's what we do. I mean, we spent the whole middle 1900s perfecting ways to get energy to individual people. And that's why there's gas lines, for instance, under the streets in most northern cities. That's pumping or piping natural gas to every house. Hot water heaters are a very efficient energy user. And the reason for that is, luckily, the thing that when you do an energy transformation, you're going to lose some energy as heat. Well, guess what? That's exactly what you're trying to do in this case. So you can make sure that you take the excess heat and use it to further your aims of heating the water. And so that's why a hot water heater is very, very efficient. When we talk about energy efficiency, here's the stat for you: 30% of all of our energy here in the U.S. is used in transportation. And here's the energy expended for different modes of transportation. And you can see that sort of the best deal, this is megajoules, so that's an energy unit per passenger per kilometer. And you can see here the passenger car with one driver is the highest energy expended. That's not good. But when you're on a train with a bunch of other people, only 1.1. So a train or a motorcycle is the best energy expended. This graphic here shows you the overall fuel efficiency of our automobiles. It's interesting to note, and we'll talk about this later on in another chapter, but CAFE standards. and you should write this down, CAFE, C-A-F-E, is an acronym that stands for Corporate Automobile Fuel Economy. No, average. Corporate average fuel economy. And that's those miles per gallon things on the stickers on all the cars when you go to a dealership and take a look at them. CAFE standards have been enacted to force dealers to make more fuel efficient cars. Kind of a crazy idea, because if America doesn't want them, America's not going to get them. Buy them. In the CAFE standards calculation, light trucks, and this would include SUVs, is not included in the calculation. So they're in a special category. And you can see we did great things in about, I don't know, about a 10-year span here, where our fuel efficiency went way up, whether it was cars or SUVs. You can see here both is just an average of the two, and this SUV number pulls down the car so that when you have both here, that's what you end up with, kind of an average in miles per gallon. Over on this axis is kilometers per liter. Same idea, but that's using metrics. Anyway, how do we get this? We got this big jump because of the introduction of CAFE standards, Corporate Average Fuel Economy standards. And we'll talk about that when we get into the different laws that are involved. All right, I think I'm going to move on. I think I'm going to continue here with electricity and talk to you about how we get our electricity. And there are a couple of quick little videos for you to watch about cogeneration. Let me see what's coming up here after. All right, I think I've changed my mind. I think I'm going to end this video here, real short and sweet, and we will talk about electricity generation in the next video. All right, bye for now. Take care. See you tomorrow.